coming out of the wall. So this is 50 pounds per square inch, 50 PSI gas source, air and oxygen, okay? You'll see this system here, that is a dehumidifier. So if you see water in this, there isn't any, be very afraid, okay? Because if that water gets into this, that's about a $5,000 maintenance bill, okay? How much do you think this thing costs? All the bells and whistles.
60,000.
Not quite that bad.
45,000.
About $40,000, $30,000 to $40,000. Now I can get you other ones that'll cost you less,
I don't know.
but for this bells and whistles, and it's well worth it. Because I can use this ventilator, okay, as a manager, so it's pneumatically powered, but electronically controlled. I have to have power. I have to have electrical power because this thing operates as a computer, okay? Just inside the ventilator here, the air and oxygen come to a block, okay? And that's your FiO2 control system. And it has what's called a crossover valve. If my oxygen goes bad, the sensor in here will pick up the fact that I'm using room air where I don't have oxygen, and it will alarm, okay? So since all we have is air, we'll only do this on 21% in order to keep, in fact, some of the ventilators are still gonna alarm because they don't see oxygen because of the analyzer, so we just ignore that. But if it loses pressure, it will still operate off of the other one. So that's a safety element. On the other side of the blender is the internal pneumatics, okay? And the internal pneumatics, the 50 PSI is brought down to the operating pressure in the ventilator, which will still be somewhere, as in this one, greater than 10 PSIG. 10 PSIG, if you were to take a hose, like a fire hose, or a gardening one that you just squeeze and stuff comes out. If you take a gas pressure of 10 PSIG and apply it to the surface of your skin, you'll be lucky if you're just bruised. It may actually cut skin. So never goof around and, you know, goose your buddy with a 50 PSI gas source because you'll hurt him badly. Okay, that internal driving pressure is what is applied to the proportional solenoid valve. The proportional solenoid valve is the same thing as your faucet in your bathroom or your kitchen, okay? There's a position where it is off and there is no flow of water coming through. You can open it up and a trickle of water comes through, or you can open it all the way and stuff comes gushing through, okay? So the proportional solenoid valve is the same as that faucet, okay? That proportional solenoid valve may only move a 10,000th of an inch in 0.05 seconds. So literally, you can, once I'm going to show you how to do it, you can sculpt the inspiratory phase. You can modify it a number of different ways, okay? So sometimes, you know, you bring a glass up to the faucet and all, it's a small glass. Are you gonna turn it on full blast? No, you're not. You're gonna crack it open and let it come out slowly because you don't want a lot of spillover, do you? Okay, so the same way with this device. You look at what you're trying to do and you're going to pick the peak flow coming out of the device, okay? Faster or moderately slow. So there's a range. Just the other side of the proportional solenoid valve is a series of sensors. The first sensor is a pressure sensor, looking at the airway pressure coming out. Okay? There may be a flow device there also, and the flow and the pressure will give you tell you pressure volume coming out of the ventilator. Okay? So the back here, this is a radiator to help keep the inside. There are computers inside of here, and then there are computers inside of here, and they crosstalk. Okay, and they do different functions. The different machines with software can, do extra things. So this block here is the pneumatics. This is where the guts of the real engineering is. This is called the graphic user interface. Okay, and it swivels around. So when you position it, you're going to point it toward the door. So when you're walking in the door, you can see it. You can see the squiggly colored lines on the graphics. And if you understand compliance and resistance and flow and time, those 4 variables, you can sometimes look at the patient, walk around the bed, get over to the ventilator, and you have assessed the patient and the ventilator, and you know what the problem is. Okay, I can guarantee you. Okay, it is a real skill. Okay. Okay, so in this case, now all ventilators have some kind of patient ventilator circuit. This is the interface between the machine and the patient. This is going to be our patient in just a minute. Most of these are polyvinyl chloride circuits, and we always put a filter. This is to collect anything that comes out of this. This is really kind of superfluous, but I'm not going to argue with people. But that's where the gas comes out. Don't let the circuit ever touch the floor. Okay. Now, proximal to the patient is the Y. Okay, this is called the Y. And the Y has a port right here, and you would put a thermometer in there that would come back, and normally we would have a humidifier here. So the dry gas that's coming out of here would go through the humidifier, pick up water, humidity. And the circuits are often heated so that we don't get rain out, because as gas flows over the outside of this, it cools the tubing, that cools the gas inside the tube, and that causes rain out. Now, anytime you get water in the circuit, that you don't want to drain that into the patient, you don't want to drown the patient. So we want it to get it into the expiratory limb and drain it over into the expiratory collection device here. Now we have collection, okay, and if this starts to get really full, you can pop this off, okay. This is a simple one. Just put a towel here and catch it, and then recork it when it's done. Okay. This bacteria filter is very efficient, okay, and will block you from getting exhaled from the patient bacteria. Why do you think I want a ventilator that has an expiratory filter? Now, I'm the chief respiratory therapist. Why do I want to have this on every one of my ventilators?
So your OTC is sick.
Absolutely. So how would you feel about taking care of a multi-drug resistant tuberculin patient who has a lethal form of TB? Do you want to be breathing what he's been exhaling out?
Nope.
Hell no. So I want that on every one of my ventilators, okay? And there's some ventilators that don't have that. So I'll show you how to cheat, okay? Single patient use pitcher. And this circuit now is contaminated, okay? So you'd red bag it and put it in that appropriately. However they want you to, okay? Now that fits in there very easily, okay? But you have to lock it in place, So one of my tricks for final competency is come up to you and say, okay, yeah, the ventilator's been set up, all ready to go, here's your order, get it done. And what I do is unlock it. The damn thing won't work. How long does it take you to recognize that?
Once you realize it's not working.
Yeah, once you figure it out, you know, because you start it up, and if you're smart and you see that gate open, well, you go, oh, okay, he's screwing with me, you know? Because that's what happens. So Riverside County, it was part of my duty to manage all the hospital supply techs. Okay? What this ventilator is, here's where the on-off switch is, right here in the front. Okay. At this point, do not put anything over the end of this. Okay? If you do inadvertently, okay, block that, this thing could bounce and cause it to internally link, to seize. And this is now a paperweight until I can get Biomed out here to fix it. Okay, so nothing gets on here until you go to attach it to the patient. Now you can feel, put your hand close, feel that lice? Yeah, so there's already gas going through it. Now I'm gonna skip doing the short test on this. So we're gonna pick a new patient, and it's gonna ask you the size of the patient, okay? Because do you think the tidal volume we should put into her should be equal to me?
Nope.
Why?
Two different patients.
She's smaller than I am, right? So I'm gonna take a larger volume. Okay. So based off of our gender and height, we should identify the size of the individual and their ideal body weight. Now, I'll talk to you about that at a later time. So we're just gonna pick 70 kilo, 150, and we're gonna press continue at this point, okay? And it's gonna ask me, do I want invasive or non-invasive? Okay? Now, non-invasive means that it's like CPAP and pressure support. I know those are terms you don't fully understand yet, but it's the patient is spontaneously breathing and is going to be doing most of the work. Okay. Invasive basically means that I've got a tube and we're going to control more things. The patient's going to have less control. Okay. Now, a mode. A mode is a short way of telling us how the machine is going to operate. Every mode of ventilation has 4 phases. The trigger, the inspiratory phase, how the gas is delivered, the cycle, what ends the inspiratory phase and starts the expiratory phase, and then the expiratory phase. So that's very simple, 4 phases. The mode defines those 4 phases. Okay. So we can have AC. AC means that every breath, whether the patient is breathing and I assist, or if the patient's not breathing, I'm giving a controlled backup rate. The machine is only going to give one method of delivery. In other words, this is the way we are going to do it, there's no other way we are going to do it, this is the only way we are going to do it. Okay? Non-invasive is, well, we could do this, or we could do that, but, you know. So invasive is very strict. I can do INV, which means, well, some of the time we're going to do this, and then we're going to do it this way. Some of the time we're going to do it that way, or this, and now we're going to do it this way. So it's intermittent mandatory ventilation. Okay. I don't like that mode. I don't like it. Spontaneous is like CPAP pressure support. Yeah, it's non-invasive. Yeah, fine. Same. Okay, we got there 2 different ways. And then they have this special one they call bilevel. This is where we get into terminology problems. This ventilator calls it bilevel. Another ventilator calls it BiPAP. Another ventilator calls it APRV, and they're all the same damn thing. Okay, back to that terminology problem. But you have to understand, this guy does it different than somebody else. Okay? So those are the four major selections for mode. We'll stick with AC. You need to understand AC first. Okay? It's easier if you start off with AC and work back to spontaneous. Some people like to do it the other way around. But because you have to learn how the machine operates, it's easier to get you that anchored first. Okay? Now, so now we know the ventilator is going to uniformly, every breath is going to be delivered the same way. But do I want to center on? Do I want to focus on volume, or do I want to center on pressure? If I center on volume, I get a blood gas on him, and his CO2 is high. What do I want to do? I want to blow off the CO2. I can do the math, and if I've got control of him, if I've got him on a neuromuscular blocker or deeply sedated, where do you want the CO2, doc? Tell me, I'll do the math, I'll figure it out, I'll get it done. Okay? That's the reason for volume control. Okay? Volume control is the easiest mode to predict blood gases toward. It's the easiest mode. Okay? Or I could do pressure control. There, I'm controlling the pressures. Volume, who knows? Okay? If the patient is spontaneously breathing, yeah, that's a good mode. Okay? It's got some limitations, got some issues, but you've got some degree of control. But not as much as with volume control. Then there's another mode called VC+. And this is another one of those problems where this machine says it's VC+. That machine back there says it's pressure regulated volume control. And I will tell you right now that that's a lie, it's not volume control. But it's an advanced mode. If you don't understand volume control and you don't understand pressure control, you'll never understand VC+. So I'm trying to get you guys to understand the order of things. Okay, so we're going to go back to volume control. Okay. Now we need to tell the ventilator if the patient breathes, how does the ventilator know? Because this is an idiot savant. This thing only does what we tell it to do. How is the ventilator to sense that the patient is breathing? Well, we can use either pressure or flow. Okay? So we can use a flow trigger or a pressure trigger. Most of the time you're going to use flow trigger because it's a little bit more sensitive. Okay? Okay. So we accept all of that, hit continue, and based off of the size that I put into this uses a modified, and I know you don't need to know this, but modified Radford nomogram to calculate out what a respiratory rate tidal volume should be for this patient. Okay? It's inadequate. So either the doctor or you will determine the respiratory rate, okay, the tidal volume, the flow pattern, the flow rate, and I'm going to pick 50 because it makes the math easy. 60 is even easier math. And the FiO2 will drop down to 21%, so I don't have to listen to the damn thing. And then we'll start off with 0 feet because I want to demo something. And we'll go, oops. And for the moment, I'm going to not talk about alarms. I'm just going to take care of that. Okay? Don't put anything over here yet. Okay? You always want to connect it at that point to a patient with gas available going through. if in final competency, you haven't got this all set up and you don't have gas going through here and you attach it to a patient prematurely, you will hear the fail, go to the end of the line, you lost 10%. Okay? The gas has to be coming out of there. Because if there's no gas coming out of here and you connect the patient to it, what are you doing to him?
Suffocating him.
Suffocating him. Okay. So the ventilator senses that there's gas interruption and gas return. So it begins to cycle according to the way we told it to. Okay? So now you can see the waveforms are being generated by the patient-ventilator interaction. So this is the outcome of those settings. Okay? The graphic user interface has a number of areas. You've got your parameters across the top. Okay? This is the data you're looking to record. Okay? And then the waveforms. The waveforms, we can change the display and blow things up if you want. Okay? To look at very fine changes. Okay? We can freeze. So nothing changes. So now we can look at the thing and figure out what the Sam Hill, the squiggly colored line is trying to tell us. Okay? So I'm going to unfreeze that. And then I'm going to change the plot. And hold on. I can also totally change the graph. So I'm looking at the compliance and the resistance of my system using a pressure volume loop. Okay, so you have scalars are time-based, and then this one doesn't show you time, it just shows you the flow and the pressure pattern. Okay, so there's different graphs, and they can be changed. You know, blow them up. You can change the scale. Like Campbell diagram, which I'll tell you about later. Okay. So let's see what happens to this patient if suddenly compliance. So look at that angle, okay, and watch what happens when he suddenly has a reduction in compliance. See how it laid down?
Mm-hmm.
Oh, yeah.
Yeah. This is pattern recognition. That's all it is. If you understand what you're looking at, squiggly color lines mean. Now, how do I know you're all expert at pattern recognition? You don't even think about it because you've done it since the time you were born. You recognize other people's faces, right? That's pattern recognition. This is just another more sophisticated skill. One you might see, okay? So we have a resistance. The size of the orifice of this, see a little hole? Yeah. This is restrictive.
Yeah.
So there's a lot of resistance through this. That one, not so much, okay? And right now, I have set the compliance to a normal level. So compliance and resistance are normal. We will see that our peak airway pressure is 11 centimeters of water pressure for a tidal volume of 400 ml. Okay? This is a normal patient coming out of OR, okay, fully relaxed and all, okay? And sitting in a semi-Fowler position, okay? If we put in what's called an inspiratory pause, and I'm going to put in a long one, relatively speaking, 1 second. We're going to see on the graphs here that you can see the green inspiratory phase, and then there's a pause, and then the guy gets to exhale, that's the yellow, okay? When that flow is being stopped, there's nothing going in, nothing coming out, you can see the plateau pressure, but then when you look at it, you know, there's not much of a change in pressure. 0.4, excuse me, 0.4, I'm gonna reduce it by half. Not changing the resistance. Now, you see the peak area pressure has doubled, hasn't it? Because compliance decreased, okay? But the difference between the peak area pressure and the plateau pressure isn't that much. Why? Because there's very little resistance in the system, okay?